Hi, good morning, everyone. Thank you all for joining us today for today's outstanding PhD seminar. So today we have invited Xu Shen, who is a PhD candidate from the University of California in LA, and he specializes in autonomous driving research. So he has extensive industrial and academic experience. So he worked as a senior deep learning engineer at the Mercedes-Benz in the US, as well as a computer vision engineer in Oppo Mobile US as well. And so on top of his contributions to several high-impact commercial projects, he also has published numerous articles in the top-tier vision and robotics conferences such as CVPR, ECCV, and so on. So Wenshen has also developed a widely recognized coding framework in the connected autonomous driving domain, which is available on GitHub. For this seminar, Wenshen will be exploring the state-of-the-art technologies in autonomous driving, focusing on cooperative perception. And he will also present his recent research on this topic. So on three separate papers. So these papers will focus on how he integrates information from different agents as well as different viewpoints. Please join me in welcoming Wenshen for today's talk.
Thank you, Gabriel, for your introduction. Let me share my screen. So can you see the slides clearly?
Yes.
Okay. Yeah. First of all, I want to thank Dr. Liu's invitation to give a talk here. It's my great pleasure to get a chance to talk about my works. And today's presentation title is The Ultimate Solution for L4 Autonomous Driving, Coordinate Perception. So yeah, let's get started. So here's the agenda today. I will first introduce myself a little bit, and then talk about what is coordinate perception, and then the SOTA methods that I have developed so far. At the end of the presentation, I wish I could have some discussion, but to get some insights on the projects. So yeah, this is my background. I get my bachelor degree in electrical engineering major from both North China Electoral Park University and IIT in US with a 2+2 program. And then I went to Northwestern University to study the master degree in the EECS department. This is where I started to learn about computer vision and autonomous driving. And currently, as Gabriel introduced, I'm a PhD candidate in UCLA focused on autonomous driving. And during the PhD study, I focused on the simulation perception. If you notice, there's a 3-year gap between my master's degree and my PhD. That's because I spent 3 years in industry. I spent 1.5 years in Oppo Mobile Research Center in US as a computer vision engineer, and spent another 1.5 years in Mercedes-Benz as a senior deep learning engineer. This is my background, and now let's talk about the coordinate perception. So we know that recent progress in the deep learning has pushed the autonomous driving perception system to a new level. However, the challenges still exist for perception system. It is well known that perception system suffers a lot from the occlusions and far away distance objects. Let's take the left scenario for example. There's a live vehicle going fast along the street. At the same time, there's a boy playing with a football, and the football just dropped to the center of the street, and he wants to pick up. The left vehicle needs to stop immediately to avoid any car accident. But however, the green vehicle on the roadside just totally block its view. And there's no way for any deep learning algorithm to detect the boy because there's just no measurements. And such scenario is very dangerous. Let's take another example. The eagle vehicle here is going to turn left on a T intersection. And then there's some upcoming traffic towards its direction. It needs to stop to be safe, but the roadside parking vehicles also block its view, so it cannot see anything, which makes the scenario also dangerous. And these are the dangerous scenarios, but very common in daily life. And for this kind of scenario, it's very hard to use deep learning to tackle the challenge because there's no measurement. So how to do with this? The solution is coordinate perception. let's get back to the scenario again. Although the left vehicle cannot see it clearly, but the vehicle on the upside, it can see the boy very clearly. And if both vehicles are equipped with V2X communication equipment, then the up vehicle can share the visual information with the left vehicle. Now the left vehicle can know, okay, there's the boy just behind the green vehicle. You need to stop immediately to avoid the car accident. So this scenario, like each vehicle can leverage V2X communication to share visual information to get better performance, is called quality perception. Let's see a more intuitive example. As we see, the Eagle vehicle cannot see the upcoming traffic, but the CFAR, which is passing by, can see it clearly and share the information with the Eagle. Now we can see from a very incomplete system environment, it becomes to very complete point cloud, and thus make the scenario much more safer. So yeah, so far we have seen the quality perception is really powerful and can bring the perception system to another level, but it is very challenging to deploy in the real world. So the first challenge is what visual information should we share? So current vehicles are equipped with DSRC communication system to transmit the message. So if your visual information is too large, there will be serious delay and damage performance. As a result, your transmitted data size should be minimum while containing rich information, which is kind of challenging. And second, the vehicle can not only talk to the vehicle, but also the smart infrastructure sensors. And even for those vehicles and infra sensors type of thing, they are hung on different position. For example, the infra sensor usually hung on very high position, like the traffic light pole, which is 6 or 7 meters. That will cause very different sensor view and cause the sensor heterogeneity. And such sensor heterogeneity will cause the domain gap between the vehicle's sensor environment and the infra sensor environment. So this is the second challenge. And for third challenge, we know that GPS always has error, and including the infra GPS. If everybody has GPS error when they transmit the information to others, the others need to project the information to a unified coordinate system. And because of the post error, it will be some global misalignments and damage accuracy. And last but not least, is the synchronization issue. So we know even if the data transmission size is really small, there still will be some delay. When the Eagle vehicle receive the others, it may be already 200 milliseconds ago, which can cause the information's misalignment again. And these are 4 challenges that we have to solve before we really want to deploy in the quality perception system. And so in the ECCV paper, V2X variety vehicle to everything quality perception with vision transformers, I come up with a vision transformer to handle these 4 challenges together. So the first challenge, what to share. In this paper, we focus on LiDAR cooperation. So every vehicle only equipped with LiDAR, and they are trying to do the 3D detection. So then the most intuitive, straightforward way to share the visual information is to share the point cloud. Everybody give the point cloud to others. The others can stack together and use a convolution neural network to extract features and get the output. But this way, it will give a lot of bandwidth burden to the transmission system, because right now we know the point cloud is pretty dense. 1 second, million points, that will be too large for the bandwidth and cause serious time delay. The other way is our vehicle detects just using their own LiDAR sensor, and then detect the objects using their own sensor, then transmit the outputs, the bounding boxes positions directly to others. In this way, it's just like metadata. The bandwidth is very small, and the transmission size is small. But the question is, because each vehicle detects the objects under their own sensor environment, so it didn't really leverage the context information. There are a lot of information wasted. So in this paper, we propose another new approach to share the visual information called intermediate fusion. So first, each vehicle will extract the CNN feature from their own LiDAR points, and then they will transmit the CNN features. The others will aggregate all the received CNN features and then do the fusion and get the outputs. So in this way, there are two advantages. First, the CNN features are known to be robust for the compression. So we can compress the neural features to a very small size and then decompress on the receiver side without too much drop on the precision. And second, the neural features also contain very rich context and scenario information, although it's kind of abstract. So then it can trade a good trade-off, achieve a good trade-off between the accuracy and the bandwidth requirements. So let's have a look at the overall framework. Assume we have multiple autonomous vehicles and a smart infra on the road, and one of the vehicle will be chosen as the ego vehicle. So there will be two round communication. In the first round, the ego vehicle will share its pulse to the other AV or the other infra, and then the other AV and infra will project their LiDAR points on the ego vehicle's coordinates based on the transmitted pulse. Then they are kind of in the same unified coordinate system. And then we use CNN, which is point pillar in our case, to extract neural features and transmit those neural features to ego vehicle. And we use a simple one-by-one convolution to shrink the channel size to simulate the compression. And the decoder is another one-by-one convolution to make the channel back to the original dimension. Then the ego vehicle already has others CNN features stacked together. And the next will send the whole stack feature to the core module of the paper, V2X the vision transformer, a normal vision transformer to handle the fusion of the feature from different vehicles. And finally, there will be prediction head to get the final 3D object detection bounding boxes. And there are kind of three challenges in the whole framework. So first, the pulse is transmitted are inaccurate. So when they project the LiDAR to the ego coordinate system, there'll be some misalignment. And second, the infra is hanging on very high position. So the CNN feature it extract has a domain gap with the features in from the other vehicles. And the third challenge is when they do a feature sharing, they have some delay. So the ego vehicle receive is the features from like 100 or 200 milliseconds ago. And all of these challenges will be handled by the vision transformer in a holistic way. So here is our vision transformer. There are our V2X has three important components. The first is called the delay via positional encoding, which deal with the time delay stuff. And second is called heterogeneous multi-agent self-attention module, which captures the heterogeneous graph representation between infra and CVs, and short for HMSA. And the third component is called MSV, multi-scale window attention, which captures long-range interaction with very large global receptive field to help solve the localization error. And these three components will be connected in sequence together with other common transformers component like Lie norm or MLP. And the feature, when a feature comes into it, we'll do multiple times to fuse the feature. And now let me introduce each of the component in detail. So yeah, first let's say the heterogeneous multi-agent self-attention. So when the features from the other vehicle come to the ego vehicle, the first thing we do need is to correlate the features from different vehicle at the same spot. For example, we can see this figure. We pay attention to the same spatial index along the vehicle dimension. However, this kind of vanilla attention doesn't deal with the heterogeneity of sensors. For example, the infra usually has less occlusion, broader view, and the model should have the pre-knowledge to know which feature from infra, which feature from vehicle to get a better handling technique. So instead of treating all the features from different agent at the same time, we give the feature from different agent type, different node and edge type. For example, if we assume a spatial index from one agent is a node, then the node for infra and vehicle are different. For example, infra can be node I, and the vehicle is node way. And when they interact, like vehicle to vehicle or vehicle to infra, it should also be different. So in this way, we build up a heterogeneous graph to represent different node types and different edge type. And how can this heterogeneous graph be integrated with the transformer? We kind of do it in a very natural way. We know when we want to do the attention map, we first give a convolution to get query can value for the attention map to calculate. So, but in our case, we apply different convolution filter for features from vehicle and features from infra. So in this way, we kind of separate the node type. And then after we get the infra's query Ki value and vehicle's query Ki value, we concat them together. And next step is to multiply the Ki and query together to get an attention map. But here we add another learnable embedding to represent the edge type from vehicle to infra, or infra to infra, or vehicle to vehicle. In this way, the Q dot K become K multiplied with the W learnable embedding and multiply with the query. So in this way, we kind of embed the whole heterogeneous graph concept into our vision transformer. And the second thing is multi-scale window attention. So think about the GPS arrow. It will cause a global information misalignment. That means our model need to have the very large receptive field to capture such global misalignment. So the best thing to do is just use the vanilla transformer attention to correlate each pixel to the other every pixel. But this will be very expensive. Computation will be very high. So instead, we use a multi-scale window attention, which is little similar as a swing transformer. So we have large windows and we have small windows. For each window, the pixel will only interact with the other pixel in the same window. So the larger window will have larger receptive field to correct the GPS error, while small window will pay attention to the details. So when the feature comes, it will go to 3 different branches to apply the window attention and then merge together using just simple summation or split attention. In this way, the model has both global and local details information. And the last one is the delay-aware position encoding. We deal with this with very kind of simple way. So we use a sin-cosine position encoding to add to the features. For example, some features has 100 millisecond delay, and some feature has like 200 millisecond delay. So then we, based on the time delay, we add a sin position encoding to it to let the model know that this feature has what extent of the time delay. And yeah, we put all those together as a V2X and we collect our own simulation data set to validate our method. These are 2 scenarios we can see. One is in a city road, one is in highway. And in the both scenario, we can see that multiple vehicles and also infra show together to provide multi-view sensor data. And we have test the method under 2 settings. One is perfect setting, that we assume the pulse is accurate and everything is synchronized across the agents. So this is kind of idle setting that is not realistic enough. So we have another setting called noisy setting. So we add a Gaussian noise to the pulse arrow, and then add some fixed time delay to simulate the real world conditions. From the table, we compare with SOTA method, including disconnect from Nuix, V2VNet from ECCV, OPV2V from ICRA and FGrouper, also from Top Conference. And we also compare with late fusion, early fusion, and no fusion, which is a single agent perception. So as a result, we can see whether under perfect setting or noisy setting, our V2X variety can outperform other methods by a large margin, especially when it comes to noisy settings. Our V2X variety can even beat the second best method by around 7% on average precision. And we can also see the correct perceptions and methods are outperforming the no fusion baseline a lot, no matter what the method it is. So we also conduct some sensitivity analysis to the pulse and delay noise for our V2X variety. We can see when the pulse error becoming larger, the other method, a lot of methods are kind of dropping down even worse than the no fusion baseline, and some methods are kind of close to no fusion. But our V2X-YT can still achieve very high performance. Even when the time delay is 400 milliseconds, we can still outperform the baseline by like 10%, which shows the robustness of our method towards the real-world noise. So after finish this paper, I feel V2X-YT has a drawback. So every vehicle or infra is using LiDAR, and we all know LiDAR is expensive. So can we just use camera to perform color perception? The answer is yes. In the next paper in Coral 2022, we come up co-BVT, cooperative both-eye view cinematic segmentation with slice transformer, which is the first framework that use pure camera to conduct quality perception. So still on the road we have multiple vehicles, but in this time each vehicle is only equipped with several RGB images to cover the surrounding information. There's no LiDAR or no radar sensor. And how we do the color perception? So first, each vehicle will use some camera encoder, for example, ResNet, to extract the feature from the RGB images. And then the RGB images will be there will be a transformer applied on the RGB images features to project from the perspective view to the bird-eye view. If there is no collaborator, the Eagle vehicle will just using the CVVT transformers results and use a decoder to get a map prediction. But if there's some collaborator, then it will transmit its BV features to the others. And when the others receive the features, we'll do a spatial mapping on the feature dimension to project their own coordinate space, and then use another transformer to do the fusion. After doing the fusion, there will be another decoder to decode out the map prediction. And we can see using this framework, the map topology and dynamic objects can be predicted very well. So for the whole framework, there are two challenges. First, how can we project the perspective view to the bird-eye view, right? Because the RGB images are 2D information. And if we want to get a 3D information, it's an ill-posed problem. So that's the first challenge. The second is how can we aggregate and fuse the BE feature from different agents? Because this is obvious real-time application. So we have to make it efficiently and effectively. So to tackle these two challenges, we come up both CVVT transformer and fused BE transformer. And both of these models are using the same core module called FAX, the fused axial attention. So we argue that no matter for multi-view fusion or multi-agent fusion, the key is to correlate the features from different views or different agents effectively and efficiently. So we need both local and global correlation. For example, this vehicle is split into two cameras. And only if we have a global attention to connect these two parts, the model will know, okay, this vehicle is, these two parts are from the same vehicle. And for the local details, we can see that each vehicle can only capture part of the scenarios. And only if we pay attention to details, the vehicles, the occluded area can be merged together and become a more complete sensing. So this inspires us to design the fused axial attention, which contains a 3D local window attention and a 3D global, also we call 3D grid attention. So in the 3D grid attention, we regard a whole patch of feature as a single pixel. And then each pixel will interact with all other pixels on the different locations and different views. And for the 3D local attention, every pixel only interact with the same local window in the same agent, but also the position, the other agent's window in the same position. So in this way, we have both local and global attention. And because we kind of make the whole thing sparse, the computation is kind of linear. Now, why it's called fused axial attention? Because in the real, when we try to implement the algorithm, all we need to do is to swipe the axis. For example, here we have a tensor N HWC. N is number of agents. H and W are the height and width, C is the channel of the feature. And for the 3D local window attention, we first split the HIW to H by P multiplied W by P's number of window, and each local window has a dimension of P by P. And then we move N and the P into the second last dimension and apply the attention on this dimension. When we come to grid attention, we do the reverse way. We put the number of windows into the second last dimension, and we put the local window dimension into the first dimension. So in this way, we kind of swap the axis and do the attention on the same position. So that's why it's called fused axial attention. So here is how the effects integrate with both thin BVT and fused BVT. It's actually quite similar. The only difference is the Curie K and value are different. For thin BVT, the Curie is an BV embedding, which is a limbo embedding that represents the real-world grid. And the Curie and the K and value are the camera features computed from the ResNet. Then those Curie K and value will be applied using the FACS cross attention like I mentioned before. And such operation will be conducted for several times until it gets a BV feature. And those BV features will be delivered to other agents. And the aggregated BV features will come to self-attention. So in this case, the Curie K value are the aggregated BV feature itself. So that's the only difference of these two transformers. Here we see some results. So we conduct our model on 3 different data sets. The first is OPV2A, which is a multi-agent data set that you have seen already in the last slide, in the last topic, vehicle XYT. And in this track, we only use camera and we have multiple agents. The second track is OPV2A LiDAR track. So we argue the fused BVT can also be used for LiDAR fusion because the LiDAR already gave you the BV feature, right? And the third one is the new scene data set. So because our model can also be used for single vehicle, multi-camera setting. In that way, we only use the same BVT. And we achieve the best performance along all the 3 data sets. Especially for the using data set, we can achieve 35 FPS with the best performance. And if we move to the Tesla V100 GPU, it can actually reach to around 60 FPS, which can achieve the real-time application. So here we see a demo. This is how the performance look like in an OPV2A data set. We have the ground truth, we have the prediction, and we can see even for the road topology, it's very complicated and there are a lot of traffic. Our model can predict very well. And we also conduct the experiment on using it, like I said. And from this demo, you can see we can predict the road topology and the vehicles accurately with very fast speed. Yeah, so after I finished these 2 projects, there's a friend sent me this photo. He said, VTX Variety and CoBUT looks very fancy using sparse transformer, this fancy concept, but will they really work in the real world environment because they only kind of validated in the simulation data set. So based on the question, I want to answer him like, let's do a study and collect a new data set. So that's why I collect V2V for real, a large scale real world data set for vehicle to vehicle quality perception, which is accepted as a highlight paper in CFAR 2023, this year's CFAR. And this is the first data set in the world that supports vehicle to vehicle quality perception. And here we can see some simple. So we have 2 collected vehicles, and they will show up in the same place at the same time to collect the data simultaneously. And so in the figure A here, we project the collected LiDAR into the same coordinate space and agree them together. As you can see, the red from one vehicle and the green LiDAR from the other vehicle. And we also annotate each scenario with the HD map, as you can see from figure B. And the figure C, the satellite map shows the position, the collecting position in the real world. And in the second figure here, we can see another scenario where they are still in a kind of intersection place. And these two figures shows the front camera of the two vehicles. So this is a multimodal, multi-agent, and with HD maps data set. So let's see a comparison with the existing data set. We know there's a Kitty, there's using the Argo and the Waymo data set for a long time, but those real world data set are mainly for the single vehicle perception. And recently there's some data set for the vehicle to vehicle perception, including my own data set, OPV2V V2X set, and there's another data set called V2X SIM. But this data although are diverse and has rich information, but they are only in the simulated environment. And one of the most close data sets to us is the DEV V2X, which is a real-world data set that is accepted by CFAR 2022. But compared to DEV V2X, which is only focused vehicle to infra, we are focusing on vehicle to vehicle. So we kind of fill the gap that there's no vehicle to vehicles perception data set. And furthermore, they collect around 20 kilometers, but our driving roads contain around 410 kilometers, including multiple road type like city road, intersection, T-intersection, four-way intersection, or highway train ramp, with very diverse road types. And in total, we have 800K frames collected, and 20K of them are annotated. And we actually annote the HD map for each single scenario. So in total, this V2V for data set is very comprehensive, very large scale, and has some spatial unique characteristics. And as I told you, there are two vehicles. One is a Tesla vehicle and one is Ford Fusion vehicle. And both vehicles are remodeled to have multiple sensor, multiple iOS 3 sensor, including one LiDAR on the top and two cameras on the back and the front, and also equipped with very high precision GPS and IMU. The Tesla is equipped with the RT3000, and Ford is equipped with a Novatel GPS. And it's worth to know that the Tesla's GPS is actually the same as a Kitty data set GPS. And this figure shows the collection route of the two vehicles. So we collect the data in 3 days. The first day is in the city road, which is noted as yellow. The second day we collect in the highway, which is the red one. And third day we collect in the freeway, which is the green one. So here is how we do the synchronization, because there are two vehicles, so two different sensor systems. So we do this by we use because both vehicles have advanced GNSS modules. So their clock are very accurate and they are synchronized with navigation satellite. Then the computer is synchronized with the GNSS module, and all other sensors are further synchronized with the computer. So in this case, all the sensors are based on a common GNSS clock basis. So this will handle with a synchronization issue. And then the data pairs from different vehicles will be further filtered. So with those pairs that has offset more than 15 milliseconds will be just deleted. So all the data left is well synchronized. And we annotate the whole data set. We mainly use the LiDAR point. So we use a software called SatTag point, which is very powerful. So you can just draw a random rectangle or square here, and it can automatically annote the 3D bounding box for you. And the better part is it can also annotate the same object in a temporal dimension, which makes the annotation much more efficient and fast. So we conduct 3 different benchmarks: a cooperative 3D object detection, cooperative tracking, and sim to real. So in the 3D object detection, it's kind of similar as the V2X VIT did, but just with real world data. So we can see we have 2 different settings. One is synchronization setting, one is asynchronous setting. So the async setting is to add one more 100 millisecond time delay on the data set. Well, actually, even in sync setting, there's still some time delay. between the different sensor system. But for both of the settings, CoolBVT and V2X VIT achieve the best performance. And the performance is much better than the new Fusion, the baseline. So this kind of validates my model design in the real world setting and show that quality perception is really useful even for real world. And for the second benchmark, we are doing the quality tracking. We use a simple tracking by detection combined with a common filter. And we can see because benefit from the quality detection results, all the quality tracking's precision evaluation metric is much better than no Fusion. And for the third track, we are doing some domain adaptation study. So we know quality perception is very hard to collect. There are two vehicles or multiple vehicles. But we have a very good simulation data set. So can we just use simulation data set to train and then test on the real world data set? So this is what this track doing. We can see if we only use a simulation to train, the performance drops a lot. The CoolBVT drops around 34% compared to train on the real world. And V2X VIT drop around 38. But with some simple domain adaptation technique, the performance can be increased by around 10% for the method. So this gives a very good direction for the future research, that how to do the domain adaptation solely for the quality perception topic. And here's a demo for the dataset. As you can see, this is aggregated LiDAR data from two vehicles and their corresponding front cameras. Here's another example on the highway. And here's we visualize the data in the annotation tool, which we can see there are a lot. Actually, the scene is pretty crowded and diverse, with either low speed or high speed scenarios. Yeah. So in summary today, I introduced the three papers: V2X VIT, CoolBVT, which are kind of new models for quality perception using transformer, and the third one is V2V for real, which is the first real-world data set. And all of these three papers are based on a code base called OpenCode, which is the first first quality 3D detection code base that is open source. And the V2X VIT and the CoolBVT data is actually collected by another simulation tool I developed called OpenCDA. So basically, OpenCDA is a first open source simulation framework that supports both cooperative driving automation and regular automated driving pipeline like perception, planning, and controls, those stuff. And this whole simulation framework integrate different simulators, including Kala, Sumo, and DI Drive. It can be used to collect the simulation data set or replay the simulation or real world data set, which is quite useful. And here's a quick example of demo showing that how the simulation going using OpenCDA. We can see it contains the perception, planning, localization, and it also contains the cooperation between different vehicles using V2X communication. So welcome to use if you are interested in the quality drive automation simulation direction. Yeah, and here's all the thing I will print today. And thank you guys. And yeah, any questions?
Right. Yeah, thank you very much, Yunshen, for your very interesting talk. So does anyone have any questions? Please feel free to unmute yourself and ask ahead. Yes. But if there are no questions, then maybe I'll start with one question. So in your first paper, could I ask you about the multi-skill attention? Maybe you could just flip back to the.
This one, right? It's me stuck or people stuck? I think I lost the signal.
Yep. Is it better now?
Yeah.
Okay, so I was just curious. So when you use the attention to correct the errors, is there a way to actually identify which one is the correct one? Because you're just measuring inconsistency. Then how will you know which is the real and which one is the one the errors? Which of the sources are the one the errors?
Yeah, that's a good question. So first, the ego vehicle itself doesn't have any localization error, right? I mean, because everybody is project to its coordinates and it is using his own LiDAR sensor. So that means his feature, the ego vehicle feature, is accurate. And that actually can provide a lot of good information for them to align. And second, the different features have different Gaussian noise. So that means some part of them may have correct information and some others doesn't have. So using attention can let them align those things together. But we didn't give a very explicit ground truth on the localization here. So we just use end-to-end training. So we have the final 3D detection bounding boxes, and then we use that as the only supervised signal to train this module.
Oh, okay, I see. So I guess there's a limit to the number of agents. So for example, in your paper, there's used a number of four, let's say 4 agents, and maybe assume one agent is incorrect. So at least you have the rest to, like, by majority voting, show which is the biggest degree of consensus among, let's say, all the information you get. Yeah, I guess that could work. But of course, I mean, if you stress tested it, let's say you have at least 2 or 3 where it's a bit more ambiguous, then it might be a bit tricky to identify which source is the so-called correct source.
Yeah. So we actually didn't explicitly tell the model which one is correct. So we kind of do it in an implicit way. But that could be a very interesting direction that we also give some explicit signal to the model as a position encoding or any other ways to make the model better.
Oh, okay, right. So perhaps I'll let others ask questions first, and then maybe I can just pop in if there's
Yeah, I might have one question.
Okay, thanks, Dr. Liu.
Yeah, about your third work, you mentioned that you utilize some data domain adaptation in the evaluation.
Oh, yes.
Would you mind providing more details? Which kind of domain adaptation method is utilized here? I'm curious.
Okay. This is very similar as the a paper called domain adaptation for fast RCN, if I remember correctly. So basically, during training, the only label data is the simulation data, but we also had some data from real world data without any ground truth. Then besides the loss for the 3D detection on the simulation data set, we also had the discriminator. So we gave the model both features for both sensor measurement from simulation setting or real world setting, and then the discriminator after the backbone, the feature will be sent to discriminator, and the discriminator will tell which one is from real world and simulation. Now the goal is like our backbone to for the discriminator. So in this way, we kind of do the domain adaptation.
I see. Do you think it is possible to extend this framework to the domain generalization setting?
Generalization, you mean like even I didn't say the V2V for real world data set, like another data set?
Yeah.
Yeah, so that's a very good question. I know one of my lab mate is doing similar things, and it's kind of hard because there's not real world data set called DV2X, which has kind of very different sense environments. So in this case, if we are using OPV2 and V2V for real and then test on DV2X, there'll still be a larger domain gap. So I guess this kind of simple method could not handle the generalization very well.
I see. Yeah, thanks for the information. That's all my questions. Thanks.
Thank you.
Okay, does anyone have any questions? No questions? Oh yeah, so I was just wondering, so there's an upper limit of the number of agents that you can use to integrate, right? So your table you showed for, but you try maybe a larger number and see whether it's possible. What the limits?
Yeah, actually, I did a study in the paper. When the agent number is when the agent number exceeds 5, the performance is kind of saturated, and the bandwidth will be increased, the computation will be increased. So I would say like 4 to 5 is enough for the correct perception.
So 4 or 5, you mean 4 or 5 vehicles in the near region?
Yes. Yes, 4 and 5 agents, it kind of have the best performance. If you add to like 6, 7, the performance is quite similar.
I see. Yeah, I'm curious because sometimes in the highway here, it is easy to find that there are maybe 8 or 9, maybe more vehicles in the same region. So in that case, does that mean we would better design another module or mechanism to adaptively select the best 5 or 4 vehicles?
Yes. Yes, I think if there are a lot of vehicles, then we probably need to build a collaboration graph to choose, who to connect who. There are actually some papers that are working on this topic.
I see. Yeah, thanks. Thanks for the information.
Thank you.
I have one question.
Please.
Yeah, so it's more general. When one looks at the level of driving automation, there's 6 levels, and your title say level 4, level L4, yeah. But we are far from a level 4, right?
Yes.
It's more. I recently like watching a video, and they mentioned that actually a lot of manufacturers actually don't even try this level 4 anymore. They go back to level 3 or level 2. So in your field of research, of course, from all your work you do, you assess and really have a good handle on all the difficulties and the challenges. So what is your kind of your vision of the future in terms of really achieving level 4? There's a need of breakthrough in camera, in really machine. I mean, of course, the camera, the LiDAR are getting, it's an increase of data actually, but the processing and the making sense for in terms of safety is still far. Of course, these days when everybody talk about ChatGPT, who's like revolutionize things, do you feel like in that field there will be some big big breakthrough, or maybe some avenue where people would suddenly have some for example, I'm thinking about a lot of photonics doing the processing these days, all this deep learning. People are looking more into the, I mean, not looking more, but like there's some drive in that sense. Thanks.
Yeah, a great question. And so first, I think so although it's still a little far from L4, but there are actually some companies doing very well. For example, Waymo. I have actually taken Waymo's taxi in the San Francisco called Waymo One, and it's actually very smooth and even avoid the road constructions. And they are also working very well in Los Angeles. So I think to some point the kind of basic technology is already there, but the policy and the diversity of the scenario is limiting them. And so I think to break through to the L4, there are several key points. So first, the sensors cost. The LiDAR, I mean, Tesla only use camera, but I always think using LiDAR is kind of crucial, necessary, because LiDAR always give you the very accurate geometry information, and the camera can only guess the information, and the camera is really working not very well in the low light condition. So, but the LiDAR is very expensive, as we all know. So when the LiDAR going down, there will be a very good opportunity for L4. And second, like you said, the robustness of the model. Like we already have ChatGPT, and right now I think a lot of autonomous driving company is also researching on the big vision model, and those models may have we bring the potential, the opportunity for the autonomous driving to achieve very good perception performance, especially for the corner case and some irregular objects detection. For example, I know Meta recently just released the Stack Anything, which is kind of the first step for the real world large vision model, right? So I can see the next step, they will try to build up those kind of generalized vision model with the image and the 3D great 3D visions connection. And thirdly, the policy is another bottle. Like for example, when there's a car accident, who should to take the responsibility, right? Those kind of policy kind of host society system need to be need to follow the technology. So yeah, I think that's the kind of 3 key points. And of course, I think if our vehicle is equipped with V2X communication, that'll be much easier for the vehicle to perform well in very complicated scenarios.
Thank you. Do you see application of this not in commercial like taxi, etc., but I see sometimes like tanks and defense, for example, military or defense vehicle. When you carry very expensive equipment, etc. Do you see some side application which is more into like defense or other? Because I work in thermal camera, and I remember that actually most of those applications like LiDAR, they're very much happy to install a lot of equipment. Of course, the cost and the rest is not an issue for them.
Yeah, I mean, of course, maybe I say maybe it's kind of easier for the military to use those kind of technology, as they really don't need to deal with such complex environment, right? So I think, for example, the perception, the object detection stuff, the tracking could be very useful for the defense system.
Thank you very much.
Thank you. Okay, so is there any other questions?
Yeah, okay. Since there's no other questions. Yeah, thanks. Mention it's excellent work. Thanks for your presentation. It was like amazing.
Thank you, Dr. Liu. Thank you, Gabriel, for hosting this.
Thank you, Shen, for your talk. Yeah. Okay, I guess this is it. Well, everyone have a good day, and we'll see you around.
Thank you.
Thank you.
Thank you.